Welcome back to a new session of MOOC on Information Security. In this session, we will discuss program threats. We know that security implies some degree of trust that the program enforces expected confidentiality, integrity, and availability. From the point of view of a program or a programmer, how can we look at a software component or code fragment and access its security? This question is of course similar to the problem of assessing software quality in general. One way to assess security or quality is to ask people to name the characteristics of software that contribute to its overall security. However, we are likely to get different answers from different people. This difference occurs because the importance of the characteristics depends on who is analyzing the software. For example, one person may decide that code is secure because it takes too long to break through its security controls. And someone else may decide code is secure if it has run for a period of time with no apparent failures. But a third person may decide that any potential fault in meeting security requirements makes code insecure. Secure programming is a way of writing codes in software so that it is protected from all kinds of vulnerabilities, attacks, or anything that can cause harm to the software or the system using it. Because it deals with securing the code, secure programming is also known as secure coding. Types of secure programs. Many different types of programs may need to be secure programs. Some common types are application programs used as viewers of remote data. Programs used as viewers such as word processor or file format viewers are often asked to view data sent remotely by an untrusted user. This request may be automatically invoked by a web browser. Clearly, the untrusted user's input should not be allowed to cause the application to run arbitrary programs. It's usually unwise to support initialization macros which run when the data is displayed. If you must, then you must create a secure sandbox. Application programs used by the administrator or root. Such programs shouldn't trust information that can be controlled by non-administrators such as local servers, also called daemons, and network accessible servers, sometimes called network daemons. Web-based applications, including CGI Scripts. These are a special case of network accessible servers, but they are so common they deserve their own category. Such programs are invoked indirectly via a web server which filters out some attacks but nevertheless leaves many attacks that must be withstood. Applets. Applets are programs downloaded to the client for automatic execution. This is something Java is especially famous for, though other languages such as Python support mobile code as well. There are several security viewpoints here. The implementer of the applet infrastructure on the client side has to make sure that the only operations allowed are safe ones. And the writer of an applet has to deal with the problem of hostile hosts. setuid or setgid programs. These programs are invoked by a local user and when executed are immediately granted the privileges of the program's owner and or owners group. In many ways, these are the hardest programs to secure because so many of their inputs are under the control of the untrusted user and some of those inputs are not obvious. Fixing faults. When a human makes a mistake called an error in performing some software activity, the error may lead to a fault or an incorrect step, command, process or data definition in a computer program. For example, a designer may misunderstand a requirement and create a design that does not match the actual intent of the requirement analyst and the user. This design fault is encoding of the error and it can lead to other faults such as incorrect code and an incorrect description of the user manual. Thus, a single error can generate many faults, and a fault can reside in any development or maintenance product. A failure is a departure from the system's required behavior. It can be discovered before or after system delivery, during testing, or during operation and maintenance. Since the requirement documents can contain faults, a failure indicates that the system is not performing as required, even though it may be performing as specified. Thus, a fault is an inside view of the system as seen by the eyes of the developers, whereas a failure is an outside view, a problem that the user sees. Not every fault corresponds to a failure. For example, if faulty code is never executed or a particular state is never entered, then the fault will never cause the code to fail. Unexpected behavior. The inadequacies of penetrate and patch led researchers to seek a better way to be confident that code meets its security requirements. One way to do that is to compare the requirements with the behavior. That is, to understand program security, we can examine programs to see whether they behave as the designers intended or users expected. We call such unexpected behavior a program security flaw. It is inappropriate program behavior caused by a program vulnerability. A flaw can be either a fault or failure, and vulnerability usually describes a class of flaws such as buffer overflow. In spite of the inconsistency, it is important for us to remember that we must view vulnerabilities and flaws from two perspectives, cause and effect, so that we see what fault caused the problem and what failure, if any, is visible to the user. For example, a Trojan horse may have been injected in a piece of code flow exploiting a vulnerability, but the user may not yet have seen the Trojan horse's malicious behavior. Thus, we must address program security flaws from inside and outside to find causes not only of existing failures but also of incipient ones. Moreover, it is not enough just to identify these problems. We must also determine how to prevent harm caused by possible flaws. Types of flaws. To aid our understanding of the problems and their prevention or correction, we can define categories that distinguish one kind of problem from another. The inadvertent flaws fall into 6 categories: validation error or incomplete or inconsistent, domain error, serialization and aliasing, inadequate identification and authentication, boundary condition violation, other exploitable logic errors, non-malicious program errors. Being human, programmers and other developers make many mistakes, most of which are unintentional and non-malicious. Many such errors cause program malfunctions but do not lead to more serious security vulnerabilities. However, a few classes of errors have plagued programmers and security professionals for decades, and there is no reason to believe that they will disappear. In this section, we will consider 3 classic error types that have enabled many recent security breaches. We explain each type, why it is relevant to security and how it can be prevented or mitigated. Buffer overflows. A buffer is a space in which data can be held. A buffer resides in memory. Because memory is finite, a buffer's capacity is finite. For this reason, in many programming languages, the programmer must declare the buffer's maximum size so that the compiler can set aside the amount of space. Suppose that a malicious person understands the damage that can be done by a buffer overflow. If the buffer overflow into a system code space, the attacker merely inserts overflow data that corresponds to the machine code for instruction. Buffer overflows can affect all types of software. They typically result from malformed inputs or failures to allocate enough space for the buffer. If the transaction overrides executable code, it can cause the program to behave unpredictably and generate incorrect results, memory access errors or crashes. Incomplete mediation. Incomplete mediation is another security problem that has been with us for decades. Attackers are exploiting it to cause security problems. In this attack, attacker supplies wrong type of data in wrong length. It is easy to exploit, but it has been exercised less often than buffer overflows. Nevertheless, unchecked data values represent a serious potential vulnerability. One possible consequence is that the system would fail catastrophically. Another possibility is that the receiving program would continue to execute but would generate wrong results. Time of check to time of use. TOC TTOU errors. Time of check to time of use states that race condition can occur if the state of the system changes between the moment when some condition was checked by a process and the moment when the action was taken based on that condition by the same process. Errors can occur when the status changes unexpectedly, either maliciously or unintentionally between a check and a subsequent operation. A TOC TTOU attack exploiting such conditions can lead to privilege escalation, allowing unauthorized access to resources such as read and write access, as well as avoiding log and audit controls. This sort of attack is difficult to detect. It requires not only looking for evidence but also determining whether it could be caused by TOC TTOU. The root cause of many TOC TTOU vulnerabilities lies in the lack of concurrency control in an operating system's file system API, and so it's not a problem that's easy to resolve. Most operating systems change the order that instructions and processes are actually executed to improve efficiency. A programmer has to achieve atomicity of two operations using an API that isn't designed for such a purpose. The challenge therefore is ensuring the file system state managed by the operating system cannot change between two system calls. Most Unix systems have adopted variants of common file system calls that operate on file handles rather than file names. These calls end in "at", such as openat and stateat. Because file handles are a private mapping to a file, they cannot be changed by another program and so are not subject to race conditions with other applications. Another preventive measure when working with a single file is to lock it before the check as opposed to afterwards, so the resources as checked is the same as it is when in use. However, file locking can't automatically roll back a failed operation, which requires transaction support by the operating system. A simple example is as follows. Consider a web application that allows a user to edit pages and also allows administrators to lock pages to prevent editing. A user requests to edit a page, getting a form which can be used to alter its content. Before the user submits the form, an administrator locks the page, which should prevent editing. However, since editing has already begun, when the user submits the form, those edits which have already been made are accepted. When the user began editing, the appropriate authorization was checked and the user was indeed allowed to edit. However, the authorization was used later at a time when edits should no longer have been allowed. Malicious code. Malicious code is unwanted files or programs that can cause harm to a computer or compromise data stored on a computer. By themselves, programs are seldom security threats. The program operates on data, taking actions only when data and state changes trigger it. Much of the work done by a program is invisible to users who are not likely to be aware of any malicious activity. However, since users usually do not see computer data directly, malicious people can make programs serve as vehicles to access and change data and other programs. Malicious code can do anything any other program can, such as writing a message on a computer screen, stopping a running program, generating a sound, or erasing a stored file. Or malicious code can do nothing at all right now. It can be planted to lie dormant, undetected until some event triggers the code to act. The trigger can be a time or date, an interval, for example after 30 minutes, an event, for example when a particular program is executed, a condition, for example when communication occurs on a network interface, a count, for example the 5th time something happens, some combination of these, or a random situation. In fact, malicious codes can do different things each time or nothing most of the time when something dramatic on occasion. Malicious code runs under the user's authority. Thus, malicious code can touch everything a user can touch, and in same ways. Users typically have complete control over their own program code and data files. They can read, write, modify, append, and even delete them. And well, they should. But malicious code can do the same without the user's permission or even knowledge. Kinds of malicious code. Malicious code or rogue program is the general name for unanticipated or undesired effects in programs or program parts caused by an agent intent on damage. This definition excludes unintentional errors, although they can also have a serious negative effect. This definition also excludes coincides in which two begin programs combine for a negative effect. The agent is the writer of the program or the person who causes its distribution. The terminology of malicious code is sometimes used imprecisely. A virus is a program that replicates itself and pass on malicious codes to other non-malicious programs by modifying them. Moreover, a good program can be modified to include a copy of the virus program. So, the infected good program itself begins to act as a virus, infecting other programs. The infection usually spreads at a geometric rate, eventually overtaking an entire computing system and spreading to all other connected systems. Various classifications of malicious code include viruses, worms, and Trojan horses. Viruses have the ability to damage or destroy files on a computer system and are spread by sharing an already infected removable media, opening malicious email attachments, and visiting malicious web pages. Worms are a type of virus that self-propagates from computer to computer. Its functionality is to use all of your computer's resources, which can cause your computer to stop responding. Trojan horses are computer programs that are hiding a virus or a potentially damaging program. It is not uncommon that free software contains a Trojan horse, making a user think they are using legitimate software instead of the program is performing malicious actions on your computer. Malicious data files are non-executable files, such as a Word document, a PDF, a zip file, or an image file that exploits weaknesses in the software program used to open it. Attackers frequently use malicious data files to install malware on a victim's system, commonly distributing the files via email, social media, and websites. Any program which does malicious tasks is known as program threat. If a program installed in a computer can store and send user credentials through network to some hacker, it is a program threat. An overview of some well-known malicious programs is discussed in this session. The important ones like viruses, worms, Trojans will be discussed later. Hope you enjoyed this session. See you next time. Bye.